Hey guys, this is Joey with TechStar, and I'm here to give a TechStar technical talk. This is what we call our T3 series. This one's on level, specifically on radar and radar technology. This is meant to be a pretty short discussion, just maybe 5 minutes long or so, just talking a little bit about radars. I'm currently sitting, you can probably see it in my background, inside of our training facility. So TechStar has a full training facility. We have 3 vessels with lots of different level technologies on them, as well as flow technologies. So let's get started. A little bit about radar and how radar works. I'm going to start off with a little bit on pulse radar. So in this picture here, you can see we have a radar mounted at the top of a vessel. And what is a radar? A radar is, it's in a level measurement, is just a line of sight instrument that shoots out a microwave signal. The microwave signal goes down into the measurement range into the vessel, hits whatever it's going to reflect off of. In this case, it's process. It comes back, and we measure how long it took to do that. So these packets travel at the speed of light, and it's a pulse packet that goes down, hits the level, comes back, and we measure how long it took to do that. What we generate out of that is what we call an echo curve. Okay, that is a visual representation of our actual measurement. So in this picture, you can see the large echo right here indicates where our product is in this measurement. This equates to a distance measurement. This distance measurement can then be calculated out to be percent of vessel measuring range. So if my 0% is down here and 100 is here, it'll tell me what percentage full I am. It'll give me measuring height or whatever kind of units I'm looking for. So let's go a little bit into the 2 different technologies with radars. One of those is a frequency modulating continuous wave, FMCW. So FMCW is when you basically have a continuous microwave signal that will be from, in this instance, we'll say from 78 gigahertz to 82 gigahertz, and it's a continually shifting frequency. The phase shift is change over to a time of flight measurement. Okay, so it's basically proportional to the time of flight. A little bit about this technology is it's actually your first radars were typically frequency modulated, and today that can be seen in the automotive industry when it comes to the radars that do the cruise control. Sorry. It's the adaptive cruise control. They use that same technology in the automotive industry. So let's move on to pulse radar, which is probably the more popular for your 2-wire systems today, although FMCW is also used. So on a pulse radar is more of what I was just showing you a minute ago, where you have the microwave signal that is pretty much produced up here, shoots through the guide wave, goes down, hits whatever it's going to hit, and it takes, you can see the little stopwatch here, it measures how long it took to do that, and it calculates the distance based off of that. So very, very simple in the terms of how they work. The graphical representation that we get based off of that, which can be viewed with typically most of your radar software, is what we call an echo curve. Okay, so in this axis, you can see my signal strength. Different manufacturers will show signal strength in different ways. And then you can see down here is my distance measurement. And that's also usually done in different ways. So in this particular one, you can see my arrow is pointing right here at this echo. This is my largest echo in the vessel, and the radar is determining that as my level. These other echoes that you see here could be different things. Most likely, this is something else that is being caught in that beam path that is giving you some sort of reflection that is bouncing back into the radar system, and it's showing the graphical representation of the tank. So it's basically drawing out the inside of your tank, if you would. We perform, during setup, we perform what we call some sort of tank mapping, where we'll basically map out these other signals so that the device is only looking at the level when it's making its measurements. So when that beam comes out, it's not a laser. It doesn't come straight down and straight back up. It comes out in, we have what we call a beam angle, okay? So there's a couple different things that determine your beam angle. One of those is going to be the frequency of the device. So your higher frequency is going to produce a narrower beam angle, and then your lower frequency is going to produce a larger beam angle. The other thing that has to do with that is your antenna size. So your antenna size also plays a big role in this. So your larger antenna will give you a smaller beam angle, and your smaller antenna will give you a larger beam angle. Now the antenna size, when I say beam angle, or when I say antenna size, that has a lot to do with like so if you have, let's say, a 6-inch flanged fitting, that will be a larger than your, let's say, 1.5 or 2-inch. So we've talked about beam angle. Now we're going to talk about decay value. Okay, that's basically the conductivity, electrical conductivity of whatever this radar microwave beam is hitting. So a larger decay value item, such as water, which has got you can see here has a decay value of 80, will give you a much larger echo. Whereas something that's a smaller, like a liquefied natural gas in this one has 1.4, or oil that has 2 to 4. Oil, even though it's small like this, we're still rarely able to measure oil. Radar technology is a great technology to pick when it comes to measuring oil. A little more about what we choose to measure different products, or I guess different technologies. A couple of advantages to radars is it's not density dependent. So the radar doesn't care what your density is of your product. It doesn't care what your pressure is of the vessels of your airspace. It doesn't care what the temperature is. It just basically cares if it can see whatever it's trying to measure or not. And if whatever it's trying to measure, is it reflective? So as long as it's reflective enough for it to measure it, and as long as it can see it clearly, it's going to give you a very reliable measurement. In most cases, down to an accuracy of a couple of millimeters. So extremely accurate measurements. So what determines that echo size? We said it was decay value, right? So you can see here, I have this larger echo. Okay, that would be my larger, higher reflective substance, such as water. And then my smaller echo would be something that's not nearly as reflective. As long as I don't have noise or other objects in the range that is in my measuring range that is larger than whatever I'm trying to measure, I can measure it easily. So what's going to determine something being in the way or being inside of the measuring range? So you can see in this picture here, I'm going to get my most energy is right here in the center. So whatever is hitting that is going to be where I'm going to get my largest echoes. Okay, I'm going to get my most return, my most signal is going to come back up to my device. The stuff that's here on the outside is going to be a little weaker. So if I do, let's say I have maybe some brackets, interior brackets on the vessel, or maybe some interior piping, and it catches some of this, this could give me some small false signals. But as long as my echo coming off of my product is larger than these, we really don't care. It doesn't matter to us. So in this representation, we're basically just showing you of different installation points that you might choose. You want to if you have a choice, we don't usually have a whole lot of choices when we're choosing where we're going to mount our devices, because this is a top-down measurement. But if we do have a choice, we want to try to pick an area that's off the vessel wall enough to maybe get away from the frame. A foot's usually good enough. But we also want to make sure we don't have a lot of stuff in the bottom that's going to be within our measuring range. Now, let's say I do have heating coils, as you see in this example. That could be the lowest point that I could measure. So if my zero, where I want to put my zero in my measurement range, is above these, then it really doesn't matter that this is down here. So we're just kind of showing you different points of where we can do our measurement. We want to keep it right here in the center the best we can. So that's really the gist of what I wanted to talk about in our technical discussion here. In closing, a radar is a very reliable instrument. They're available as loop powered, many different protocols such as field bus, Profibus, Modbus, loop powered. They're not influenced by process temperature, process pressure, or density. And if you're looking for any more information, please contact TechStar. You can find us on the internet at our webpage at techstar.com. And we have a training department, service, and sales that would be more than happy to assist you in your measurement. Thank you.